So let's talk about how to actually write a puzzle file for this simulator. So at the moment, let's look at the 3x3 right here, right? You saw this last time. So this is written actually with a file that's right here. Now also I have other puzzles, like for example I have the 2x2 that I've written for this version of the simulator. I have my penta mix-up. Actually, let's go to the Pentagonal Prism first. So I have a Pentagonal Prism here. You can scramble that. And of course see the back of it too. But I also have my penta mix-up, if anybody has seen that. And so this actually works like a penta mix-up. There's some group theory math involved in here. I'll explain that at some other point. But right now I just want to explain how to write a puzzle file for the simulator in its current version. See, I'm probably going to keep changing things. There is a lot of stuff that I do keep changing every so often, but at the moment this is what it looks like, and I don't know if it'll change too fundamentally from this, because you still need certain types of data in there, but I might want to incorporate other types of puzzles, like maybe jumbling puzzles or puzzles that have moves, like geared moves or that kind of stuff. But for now this is what it is. So this cube 333 file is right here. So there are 9 pieces of information that the simulator needs from the file in order to read the puzzle. So the first piece of information is just a single number. It's the scaling factor. Now I actually want to get rid of this input into the file. I actually want the simulator to be able to read this directly from this next piece of information right here, but that's a little bit far off from now. I'll maybe do that soon, but for now you have to input it manually. Basically what this is the farthest away from the origin that any of your points is, if that makes sense. So in this one right here, so I actually wrote this 3x3 cube as, instead of going the origin at 0 and the edge and the tips of the cubes, the vertices of the cube at 1, 1, 1, and those points, I actually made it at 3, 3, 3, so that I didn't have to deal with fractional points. And so I ended up making the scaling factor as 3. Let's see what happens if I make the scaling factor 1. Oh look, it's huge. I mean, I can zoom out obviously, but it's huge, and you want it to start off at a reasonable scale, so 3. Okay, so that's the first piece of information. Second piece of information is what I like to call the location data. So this is basically giving you where each sticker actually is located in 3-dimensional space. But if you notice, some things are in square brackets, some things are in round brackets, and all this doesn't really seem to make too much sense. What does this 90 minus 90, what does all that mean? Okay, so each one of these lines right here, I mean, you could write it all as one line if you wanted to, because everything is separated by commas, but I write it as separate lines just to make it clearer in my head. Each of these lines represents one of the faces on the puzzle. So when you're writing a puzzle, you'll write each face either in square brackets or in round brackets. So this is a face, but this long thing is also a face. Either in square brackets or round brackets, separated by commas. And then the simulator will end up reading that later. So there are 2 different types of faces, right? The square bracket faces and the round bracket faces. The square bracket faces is when you're defining a face for the first time. So when you're defining everything that has to do with a face for the first time. A round bracket face is when you're defining a face for the second time. So let's just treat everything inside these square brackets as a black box for now and pretend that it defines the front face of a cube, which it does. This defines the front face of the cube. So now, once I've defined the front face of the cube, what the round bracket face does is it'll take that front face of the cube and copy it and move it around if you need it to. So inside these round brackets, I have 2 sets of instructions. One of them is 0, 1, 0 in square brackets, and the other one is 180. And what this means is take the face that you made before, rotate it around the y-axis, which is 0, 1, 0, rotate it around the y-axis by 180 degrees as your second face. Okay, and then the third line again means the same thing. It means rotate this face. It's always rotate the most recent square bracket face. So this third line is rotate face 1 around the y-axis by 90 degrees. So if this gives you the front face, which it does, then this will give you the back face. And then this will give you the right face, I believe. This will give you the left face because you're rotating face 1 around the y-axis by minus 90 degrees. Then this will give you the top face, and then this will give you the bottom face. Okay, so you define a face, then you can copy it over, rotating it around different axes. You can also translate it if you want to, and translation is instead of square brackets for the axis, it's actually round brackets. So what this would mean, if I did that, would be it would be translate this face 1 unit in the y direction. So that's round brackets, but square brackets means to rotate. Okay. Now, let's not treat everything inside this like it's a black box. Each entry inside of this definition face, and let's enter it just so it's easier to understand. This is the definition of the first face. Each entry inside of this list is a sticker. So let's do this. And they're all separated by commas. Now the way I formatted here, actually, the simulator will still be able to read it. So let's try that. The simulator can still read it. So all these spaces don't actually matter. It cuts out the spaces. As long as you have fewer than 3 spaces. So if you press enter 3 times, like one more time, it'll crash the simulator. But you can have 2 spaces here to enter keys. Okay. So each one of these is a sticker definition. And it works very similarly to how I define the face definition. So here I define a face in square brackets, and then I copy it using round brackets. Here again, I define the first sticker using square brackets, and then I copy it using round brackets. But if you notice this time, the round brackets are just 3 numbers without any brackets around them. And I actually wrote the interpreter to interpret this instruction the same way it interprets with the double brackets. It interprets it the same way. Basically what it does is, again, treat the first sticker like it's a black box. The second sticker now takes the first sticker and translates it by 2 units in the x direction as your second sticker. Now your third sticker will take your first sticker and translate it 4 units in the x direction, etc., until you end up making all of the squares in the face. Okay, so I use basically the same type of thing but on 2 different levels. Actually on 3 different levels, but I'll get into that in a minute. So first I define the face using square brackets, then I copy it around using round brackets. Inside of the face definitions, I define the first sticker using square brackets and then copy it around using round brackets. So again, putting double round brackets around a single command is the same as putting just the normal round brackets around a single command, which means translate. If I wanted to actually rotate this, I would put the square brackets and then by how much. If I wanted to do this, if I wanted to rotate it around the x-axis by 180 degrees, I could do that. And in fact, I have this command be the same as if you bracketed it like that. That's just for redundancy so that you can type things the way you want. Okay, let's put this back to how it was. It was 200. Okay, and again I said for the first sticker, so let's look into the first sticker for a minute again. Or not again, but let's look into it. So the first sticker, there are multiple ways of doing the first sticker, and it's very similar again to how the faces and how the pieces and how the stickers are defined on a macro level. This is the first point. So the first point is -1, 3, 3. And I actually drew this out. I actually did it in SolidWorks, and I, calculated everything. And we'll do that after when I show how to write a puzzle file from scratch. So you start out with the first point. So the first point is going to be -1, 3, 3. This is the x, y, z coordinate. Okay. The second point, if I wanted to, I could write this point as -1, 1, 3. And that actually means the same thing as the one before it. But I'm not doing that. I'm doing it instead in a relative way. So first I define this first point using the square brackets, and then using the round brackets, I'm saying I want to take this point and translate it by -2 units in the y direction. And then I'll take this point and translate it by -2 in the x and -2 in the y, then take this point -2 in the x. And now these 4 points create a loop, which creates a polygon, which is a square. And this square is the first sticker of the puzzle. And then again, this first sticker gets patterned around to make a face, and then the face gets patterned around to make all the faces. This puzzle only has one face type, and each face only has one sticker type. So it's actually pretty simple when you're defining everything here. Okay, let's undo all that. Hopefully all that makes sense. If anybody has more questions, please feel free to ask me. It is a little bit complicated, and I could go into it more, but you might understand it more when I make one from scratch afterwards. Okay. So this is the first piece of information, the scale factor. Second piece of information is the location data. What about the third piece of information? This is the color. These are the colors of the puzzle. What you can do is, so each line is its own face, separated by commas. I mean, it doesn't have to be on separate lines. They can all be on the same line if you want. That's okay. But I like to have them on separate lines again for clarity. If you want, instead of putting just a single tuple in here, what you can do is you can put square brackets, and you can define a bunch of tuples. So the first face has 9 stickers on it. So I can actually define 9 different colors. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 colors. This should work identically to how it worked before. Yeah. But now if I wanted to, I can change one of the colors. So let's change the color of the middle sticker. So instead of being this kind of blue, let's make it my favorite blue, which I do in SolidWorks, which is 0, 1, 10, 255. Oh look, the middle sticker is now lighter. So the way this works is that this color will correspond to the first sticker. This color will correspond to the second sticker. This color to the third sticker, etc. If you put the wrong amount of colors, the program will crash. Or again, you can just use round brackets and just make the entire face one color. It's up to you. That works similarly to the fourth piece of information, which are the normals. So this is saying that the first face right here, it points outwards in the 0, 1, 1 direction, which is on the z-axis. So it points outwards towards the z-axis. To look square on the face, you have to look down the z-axis. Okay. But you can do a similar thing here. You can, if you have on one face, if you have pieces that are oriented differently, you can do that. So you can have 0, 1, 1 for the first one, you can have 1, 1, 1 for the second one, etc. You can do that kind of thing. Now, why do I need the normals for each face? That's actually for rendering. So if you know which direction a piece is pointing, you know whether or not to render it. But I'll get into that at some other point when I explain how the actual code works. Just for now, know that I just check to see if a piece is pointing towards the camera or if it's pointing away from the camera, and I do that using the normals. I could calculate the normals from the polygons, but it's less reliable because using a cross product in linear algebra either gives you the normal in one direction or in the other direction, and it depends on which direction you define all the points around a loop. If none of that makes sense, that's okay. I could get into that at another point. But anyway, for now, just know that these are the directions that point outwards from each face. Okay, piece of information number 5 you need. These are what I like to call the rotation indices. So each one of these, again, represents for a face. This is a common theme that you'll see here. Each line is for a different face, again, all separated by commas. So let's look at the first line. So the first line, it's all in square brackets. Everything in this one is in square brackets. Or it actually could be round brackets. For this one, it doesn't really matter. For the other ones, it does. So it's just a list of lists. And each one of these individual lists tells you which moves can rotate that sticker. And then the moves are defined below here, but I'll get into that soon. So this corresponds to the first sticker, this corresponds to the second sticker, this corresponds to the third sticker, etc. Now, this means that the moves labeled 1, 4, and 5 can turn this sticker right here. So move 1, move 4, and move 5 can turn that sticker. And let's see that. Right, so that sticker is this one right here. Okay, so move 1, which is the blue move right there. Perfect, that works. What about the orange move? Oh, that works too. What about the yellow move? Okay, so all of those moves turn this one. 1 is this, 4 is this face, and 5 is this face. Because remember the order we defined them in, right? Or sorry, actually, that's not true. That was the order we defined the face data, not the move data. I'll get into that soon. But, But so that tells you which moves rotate each piece, and then these change as every time you turn it, these things actually change, not in the text file, because these are just the starting values, but they change in the actual code here. So I'll actually show that right here. I call it rote-ins. So rote-ins, I believe it's 0, 0 should give you that one. Nope, just 0. Okay, so that gives you 1, 4, 5, right? Which makes sense. That's this one. Okay, but now what happens if I rotate it? What happens if I rotate it by the blue face right here? Okay, that means that now this piece right here should rotate by face 1, face 3, and face 5. So let's see what it is now. Rote-ins 0 should be 1, 3, 5. Oh look, it's 1, 3, 5. I mean, it's 1, 5, 3, but that's the same thing. And that actually might give you a hint as to how it knows what to switch everything to, but I'll get into that after. Okay, so that's the rotation indices. That tells you basically which moves turn each sticker. Okay, 6th piece of information. This one is probably the simplest. That's just which key rotates everything. So when I press the B key, it rotates. It does the first move. When I press the G key, it does move number 2. When I press the R key, it does move number 3, etc. Okay, 7th piece of information. This tells you which axis the move rotates around. I don't actually have the capability for one single move to rotate around multiple axes. I don't have that yet. I might add that in the future, in which case this entire structure will change a little bit. But for now, this is just the axis it rotates around. So when I press the B key, it does a move that rotates around the Z-axis by 90 degrees. So these 3 pieces of information together make the move data. So this B, when I press B, it rotates, because this is the first entry of all these 3. So when I press B, it rotates every piece that has a 1 in its index, or it has a 1 as one of its indices. It rotates every single one of those pieces, and only those pieces, by 90 degrees around the Z-axis. Now, it's actually a little bit tedious to program these in, because these have to all be done manually, but once you do it, I mean, that's the only tedious part of this entire thing. But again, we'll get into that when I make a puzzle. Okay, so these 3 pieces of information, as I said, the 6th, 7th, and 8th, they give you the move data. So they tell you which move does what and what the moves are called in what order. So the moves are implicitly named 1, 2, and 3. Sorry, that's not true. 1 here, 2 here, 3 here, etc. Okay, the last one is what I like to call permu. So let's do permu of 0, 0. That should give you this first one. And what that means, and they're in a specific order, this one corresponds to the first move. Although it's not actually a part of that move, but in a sense it sort of is. It's a little bit complicated, but it's basically a permutation. And it tells you which permutations happen given a specific move. So when I do move number 1, these are the permutations that happen. So when I do move number 1, inside of the code, what happens is every single piece that has 1 as its index gets all their other indices shifted to something else. So when you get rotated by move 1, actually, I don't think that's quite true. I don't think my explanation of this is doing it justice, but it might be clearer once I make a puzzle afterwards, but I'll just explain this for now. If you do move 1, then it calls this permu, and if the piece has a 1 in its index, then it runs basically this. So what it does is it takes, if it has a 1, it replaces it by 1, obviously. If it has a 2, it replaces it by 2. So those don't change. If it has a 3, it replaces it by 5, I think. Or it might be the other way around, but I think it's that way. If it has a 4, it replaces it by 6. If it has a 5, it replaces it by 4. And if it has a 6, it replaces it by 3. So this is all implicit. I did do this in a dictionary to start with, where I went 1 goes to 1. I went 2 goes to 2. I went 3 goes to 5. I went 4 goes to 6, etc. But this is easier to type out, although it's implicit. So it might be better to do a dictionary so that you can be more versatile. At the moment, you have to name the moves in order from 1 onwards. If I did like a dictionary, you wouldn't have to name them like that. You could name them whatever you want. You could name them letters if you wanted to. So this wouldn't have to be 6. It could be E if you wanted it to. But at the moment, it's not. Okay, so I hope all that made sense. That right there is all of the data that goes into making this puzzle right here. It's very versatile. It's not necessarily as versatile as I'd like, but it is very versatile. So you can make a wide variety of things. For example, using this format, as I showed before, you can get my penta mix-up. And at some other point, I'll go into detail how I made this file, but I'll make a simpler one for now.